Okay, so I'll bring this a little closer. I'm recording this, so I'll put it on the classroom later. And these notes are on the classroom. All right, so we're going to talk about chemical versus physical changes, just as a reminder. Is this okay, or do you want the lights off? Can you guys see this okay, or should I turn the main ones off? All right, so chemical and physical changes are a little bit different. Chemical changes are something that produces a new type of matter, right? We kind of went over this a little bit at the beginning of the class, at the beginning of the course, rather. And that new kind of matter is going to have different properties. So, for example, when we did that hydrogen balloon and we lit it on fire, the hydrochloric acid is something that is really corrosive, and it can, eat through metal and everything, and it's liquid. And then the zinc is a solid, and we put that in there. And then what we got was a couple things. There was a liquid produced, but also a gas, which has the ability to explode pretty intensely with the addition of fire or heat. So it was a new type of matter. It's a gas, and it had very different properties from the original. So that was really obviously a chemical change. And we can call chemical changes chemical reactions. So some clues that we can use to indicate a chemical change. Bubbles of gas given off, so we've got a really obvious state change. Usually without changing the temperature, so this doesn't count for like boiling water, for example. Heat or light are given off, so that usually means, do you all remember the word exothermic? Yeah. So heat or light are given off when reactions are exothermic. Sometimes something will cool down quite a bit when it's endothermic as well. So some kind of heat change. A color change occurs. And these aren't always applicable, right? Because sometimes you're going to mix food coloring and you're going to get a new color, but there wasn't a chemical change. But these are cues that we can take to see, like, maybe there was one. A precipitate forms from a solution. Precipitate is a solid. So if you mix two liquids and you get a solid, that's called a precipitate, and that's a really good indicator that you've got a chemical reaction that's occurred. You've got a new state of matter, and often it'll be a different color. Got some really fun precipitate reactions we'll do in the chemical reaction lab. And then a little note: decomposition and electrolysis of compounds are chemical changes, is a chemical change. So decomposition reactions, like hydrogen peroxide in that elephant toothpaste reaction that we watched, where hydrogen peroxide decomposes into oxygen, hydrogen, and water, and creates gas. That's a chemical change. And do you remember the electrolytic cell that I made, where we could see the pink indicating a acid on one end and the bubbles on the other side? So that was an electrolysis reaction, and that was also a reaction, a chemical change. Okay, physical changes. Again, these are changes in a substance where no new substances are formed. And you guys did a whole sheet on this earlier in the year where you looked at different things and identified, is this a chemical reaction? Is this a physical reaction? Do you all remember doing that? Okay, awesome. Before spring break feels like a really long time ago. Okay, so examples of that: crushing, tearing, breaking, diffusion of something, so something like moves through the air or water, mixing of things, changing of state, so boiling water, freezing water into ice. All of the separation techniques that we used are actually physical changes. So we did and talked about some different separation techniques. They're physical changes. So those really rely on keeping the compounds intact, right? Like we want to separate compounds. We don't want to make new ones. So all of our separation techniques were physical, not chemical. For example, the distillation, you're getting something to its boiling point. You're changing its state into a gas and then recondensing it. Physical changes. Okay, and recalling changes of state, matter can be changed to one state or another by the addition or removal of energy. And then a change of state can be either a physical or chemical change. And a really good hint to tell you that it's chemical rather than physical is you did not add heat, you did not take away heat. That's a really good indicator to say this change of state was a chemical reaction. Energy, anything that's not matter. And can cause a change in matter. So light from the sun can cause plants to grow. It can cause melting of an ice cube. That's a form of energy. Okay, can I go to the next page? Okay. We all remember this chart here, the solid, liquid, gas, and the different states and how they change. So that you can have that for reference. An example of some different changes. When moth flakes are heated, they change from a solid to a liquid. And this is just a chemical that's in flaky form. This is a change in state. Therefore, a physical change has taken place. It can be reversed by just cooling those flakes back down. So you can reverse a physical change quite easily as long as you capture everything. Like if you take a thing of water and you boil it, you've got to capture the gas if you want to reverse that state. But you can always reverse physical changes. Sometimes you can reverse chemical changes, but not always. When sugar is heated, it doesn't melt. It bubbles. And you get a black solid and a colorless liquid. If you try to mix them back together, you get a black wet mess, and it's not like the original material. Have you guys ever burnt sugar? No? Okay, I might take some sugar and sulfuric acid and combine them to show you guys. It's really cool. So therefore, because you can't reverse it just by changing the temperature, a chemical change has taken place. So basically, it's just really important to understand that chemical and physical changes are different things. Chemical changes are the rearranging of atoms, and the rest of this unit is really going to be based on that. We're going to be talking about chemical, not physical changes. It's a really good look. Yeah. Okay. Do you guys feel comfortable with this? There's an activity that I have, but I don't really feel it. Do you guys feel like you need the review on the differences? Or are you okay? Do you guys feel okay with your ability to identify chemical and physical changes? Does anybody want practice on that, or are you okay? Yeah? Oh, okay. All right. Yeah, let's just keep going and talk about chemical equations for a minute. And then while you guys are doing some questions, I'll get out some. I'm gonna just make a note to myself. I'm gonna get out some sulfuric acid and sugar because the sugar chemical change is a really cool thing. Okay, chemical equations. So these should be somewhat familiar from grade 10, but it has, of course, been a while. So it might be a little bit of a like throwback to quite a while ago. Okay, we're not going to do that. So a chemical reaction equation is an equation that shows the chemicals that were used up and the chemicals produced. During a chemical reaction. Does anybody remember the name for the chemicals that are used, the like sciencey word for that? Yeah, reactants. Nice. So we get reactants are the chemicals that we use up, and then products is what we get. So we're always going to be writing our reactions as reactants to products, and we'll just have a little arrow in between them to differentiate and show how the atoms are rearranged. The interpretation of that arrow is as time passes. Reactants and products both exist as time passes. So as time goes on, first of all, you've got just your reactants, and then you've got some mixture of reactants and products, and eventually, in a perfect world, you've got just products. Often that's not the case, and it actually takes quite a bit for the products to be produced. But yeah, that's kind of the ideal system is reactants, time, products. Sometimes you have to add a lot of like pressure or heat to actually get those products perfectly, but it's this is the ideal situation. Okay, two types of equations. Word equations and formula equations. So what you're probably more familiar with from grade 10, depending on what you did and who you had, is probably formula equations where you're seeing like H2O goes to H2 and O2. But there's also word equations, which are really important to be able to determine. And this is why you're going to say word equations. This is why we've spent so much time on naming and practicing that. So in word equations, we're going to see our reactants on the left, our arrow, so produces, or yields might be said in a word problem. So it might say water produces or water yields. And then we've got our products on this side. So you could see things written out as a formula, or you could see them in words like this. Formula equations. This is important, these numbers here. Do you guys remember why these numbers are important? No? You have to have the same number of atoms on your reactant and your product side, and we'll talk about why that is later. But just know that these numbers that are large and in front of things are called coefficients. And those coefficients mean how many of that molecule you have. So that 2 means you have 2 waters, 2 H2Os. And then the littler numbers are subscripts. You all know those because we've been looking at them quite a bit already. That is how many of the specific atom next to it there are. So this number means there's 2 H2 molecules. This number means there's 2 hydrogens. So this whole thing, 2H2, if I were to draw that out, it would mean that there is two H's attached to each other, and there's two of those molecules. So the coefficient says how many of the molecule there is. The subscript means how many of that specific atom in it are. Does that make sense? All right, coefficients, number of molecules present. An example, 2 water molecules produce 2 hydrogens and 1 oxygen molecule. And then those subscripts refer to the number of atoms present in each compound. So, example, in our formula equation up there, water has got 2 hydrogens and 1 oxygen atom. But when you put water in a chemical equation, and add coefficients, the number of atoms changes. So when I say I've got 2 H2Os, like up in our formula here, 2 H2Os, I no longer just have 2 hydrogens, I have 4. So that's what that means. So in this chemical equation of H2O, there are 4 hydrogens. And there are 2 oxygen atoms with the coefficients included. Yeah. Which part? Refers to the number of molecules, 2 molecules. Oh, 2 water. Oh, no. So this is a hydrogen molecule and this is an oxygen molecule, but we know that hydrogen and oxygen are both diatomic. So when I say oxygen molecule, it's got 2 atoms. Do you guys remember those? Yeah. So although it's 2 hydrogen molecules, that is 4 H atoms. Does that make sense? Yeah. Okay. Okay, conservation laws. Okay, so some words that we're going to need to know are system. So a system is the part of the universe being studied in a given situation. So sometimes a system is going to be a beaker with sugar and water in it. Sometimes the system is going to be a forest and the trees and the carbon dioxide and the oxygen. So a system is just what part of the universe is being studied. So it often in chemistry will refer to reactions as systems. A closed system is a system in which matter cannot enter or leave. An open system is a system in which things can enter or leave. So a closed system could just be a beaker with a lid on it. An open system, beaker without a lid. Forest, open system. Forest in a bottle, closed system. Okay, so in an experiment, if an experiment examines how a beaker full of hot liquid cools down over time, the system is going to be the beaker and the contents of it. If it involves a beaker of hot liquid cooling and transferring its heat into the air inside of a box, so it's just gotten a little bit more complex, the system now is the beaker, consists of the liquid, and the air in the box. So it's just the system is widening a little bit. A beaker full of boiling water, no lid on it, is an open system. But if the beaker and the water are considered to be the system, and the beaker is on the hot plate, heat is able to enter. So that's energy. It's able to enter the beaker and the water, that system. And water vapor is able to escape. So depending on, oh, whoops. Beaker, hot liquid, and analog. Water vapor to escape. Depending on the type of experiment. Oh, sorry, I put this in a weird order. Sorry, this is in the wrong place. Just ignore that. Okay, so a beaker full of boiling water is an open system. The beaker and the water are both considered to be in the system, and the beaker's on the hot plate. Heat can transfer. So this is an open system because our water vapor is escaping. A sealed glass tube, however, that contains hot water is an example of a closed system with respect to mass. So no matter, no material can get in or out of the sealed tube. So closed system, specifically matter can't get in and out. So it's okay if there's heat. Heat can be transferred, energy can be transferred, just no matter. Open system, things can move in and out. So this is just a really easy example of an open versus a closed system. We just put a lid on the exact same thing and it becomes a closed system. And that gets really important later on. Okay, so I'm going to get you guys to work on these two questions, page 106, numbers 1 and 2. And I'm going to go get a couple chemicals and do a couple examples of experiments. Or year. Okay. So the law of conservation of mass, it smells so much like sugar in here now. The law of conservation of mass, the total mass of a closed system does not change during a chemical reaction. So atoms are rearranged, but the overall mass doesn't change. So we saw in that closed system with the lid on, the zinc and the hydrochloric acid, the mass didn't actually change when there was a lid on. And that's because the total number and type of atoms in that closed system does not change. during a chemical reaction. So this is a very important concept in chemistry, the conservation of mass. You cannot create or destroy matter. Our reactants are just being rearranged into products. So it's a similar concept to the law of conservation of mass, as law of conservation of atoms. Oh yeah, so the conservation of atoms is very similar to the conservation of mass, in that no atoms are created or destroyed. Just rearranged. So in that reaction, in that burning of that sugar, that sulfuric acid reacting with that sugar to create that carbon tower, there was no matter, no atoms were created, no atoms were destroyed. We just rearranged it. So the sugar and the sulfuric acid, those molecules just collided and did different things. And now we've got a different compound with different properties. So in this example, we've got CH4, methane gas, combined with oxygen, and it forms the products, carbon dioxide and water. So as you guys can see here, these coefficients tell us that we actually have the same number of carbons on both sides, of hydrogens and oxygens on both sides. So we have 2 oxygen molecules, which are all made up of 2 oxygen atoms. So there's 1, 2, 3, 4 oxygen atoms. And then on this side, there's 2 in this 1 carbon dioxide, and there's 2 in this in these 2 waters. So if you total the number of atoms on each side, they add up to the same. Does that make sense? Okay, sweet. There's also the law of electrical charge. So the total electrical charge in a closed system does not change. During a chemical reaction. So our electrical potential or charge does not change during that reaction. And then there's the law of conservation of energy. So what this means is the total energy in a closed system does not change during a chemical reaction. The relative amounts of the type of energy might change. But not the total amount of energy. So do you guys remember how energy is stored in chemicals? I think this would be probably from grade 10. Energy is actually stored in chemical bonds. So that's a potential energy type. When energy is stored in a bond, it's potential energy. And then in this example, that potential energy was converted into a type of heat energy. So that heat was given off. As you could see, like it caused the sugar to burn, that reaction. And the beaker actually got quite hot. So the chemical energy, the chemical potential energy stored in those bonds turned into thermal energy. So the total energy didn't change, it just changed forms. So we do get a lot of form change, but we don't get an actual energy change. These laws could not be seen to be true at the beginning. There weren't proper testing procedures, and reactions weren't very well understood. So if you just were a chemist like back in the 1800s and you took that sugar and that sulfuric acid and you combined them and you got all this heat, you'd be like, this is producing energy. But what they didn't know was that energy was stored in bonds before. So they didn't know that that this conservation of energy law existed or electrical charge. So all of these things had to be proven over time. Gases given off in reactions made it look like there was a decrease in mass. So if you're just looking at these things happening, these chemical reactions, you're not actually going to realize like what's going on a chemical level, and you might think that mass changes, but as soon as you make that closed system, we can understand these reactions better. So in order to study reactions properly, they do have to be in closed systems. And there are some special cases where matter is converted to energy. So an example of that would be in nuclear reactions, which are like a really, really great form of energy, really useful. And that's when you're actually splitting up the nucleus, the protons and the neutrons. So that is a special example where you do see matter converted to energy. But anything that we're looking at, we're going to be seeing just rearrangement of atoms. So just these laws are very important to what we're going to be doing, especially conservation of atoms. So those first two are going to be like very, very important to what we do over the next unit. And then from there, we'll also talk about these two, the 3 and 4, electrical charge and energy. But really, those two first ones, you cannot create or destroy matter. Atoms are just rearranged. Cool. Okay, so page 107, questions 3 to 6, I want you guys to work on. And then what time is it? 2:29. Yeah, so I'll give you a little